Rita Dolesi, if you're here, please make yourself known. And otherwise, we're going to proceed with a talk by Saavik.
I am connected remotely.
Oh,
is that Rita?
Remotely.
Yes, it's me. So I'm supposed to give the talk remotely, but if you postpone my talk, it's okay.
I think we'll proceed with you since you have gotten up the stairs successfully and are standing and ready. Okay,
How's the liability insurance here?
Yes. Looking forward to the talk by Saavik on astrophysics and EMRIs.
Thanks, everybody. And I'll just start by getting, I think, the most important question out of the way. I'm working on surgery number 4 after leg break number 3. This is hopefully the last one. I'm about halfway through 6 weeks of non-weight bearing, and I was not expecting to be non-weight bearing. So thanks, everybody, for bearing with me. Okay, so we've already had a lot of talk about acronyms. I'm going to throw a bunch more at you today, but hopefully I am going to define them for you. And I know we have a pretty diverse audience in terms of background. I am fundamentally an astrophysicist, certainly not an engineer. So I am going to talk to you today about the astrophysics of extreme mass ratio in spirals. And in order to do that, we have quite a number of additional acronyms here. And I'm gonna go through them and some more. So just a brief outline. I'm gonna talk to you about nuclear star clusters, which are those NSCs, because they are a critical ingredient in extreme mass ratio in spirals. And then I'll actually get on to the LISA sources that we are all very excited to see. And also their connection to tidal disruption events, abbreviated TDEs. I will also be talking about active galactic nuclei, or AGN. For those of you who have not grown to know and love AGN, I regret to inform you that you're going to have to figure out what that zoo is actually all about. So we'll get there. And I'm also going to talk about a very new, exciting source, relatively new, newly discovered quasi-periodic eruptions, or QPEs, and also similarly relatively new changing look quasars. So first, let's start with the nuclear star clusters. Hopefully everybody has seen something like the image on your left of our own galactic nucleus. And the thing that I want you to notice is that there are many stars orbiting. Their orbits are eccentric and, at least by eye, look kind of maybe not super directional, maybe vaguely isotropic. It's not true in detail, but there's stars that are orbiting very close to Sagittarius A star at all kinds of orientations and eccentricities. And our own galactic nucleus is not especially unique. On the right is a figure from Neumeier's review on nuclear star clusters. On the horizontal axis is the stellar mass of galaxies. And you can see sort of in the 10 to the 8 to 10 to the 10 region where you might expect to find 10 to the 5 to 10 to the 7 supermassive black holes. In their nuclei, the occupation fraction is quite high regardless of galaxy type. And also note that these are to be regarded as lower limits. And so nuclear star clusters are basically ubiquitous around the types of SMBH masses that LISA will be able to probe EMRIs. So how do we figure out how many EMRIs we're going to see? I'm going to walk you through the basics of relaxation theory. Don't relax so much you fall asleep, please. But this is, I think, a very helpful plot to keep in mind. There's many versions of it in the literature. I stole this one from Rem and Giacomo. But on the horizontal axis, we have the semi-major axis of an orbiter, and on the vertical, we have the pericenter. You can also think of this as the eccentricity or the angular momentum on the vertical axis and the energy on the horizontal. And of course, you can't have a pericenter of your orbit that's larger than your semi-major axis, so we have this nice one-to-one line. And things that are in the outskirts of your nuclear star cluster might be on roughly circular orbits, but as time passes, they interact through a variety of mechanisms, the most important of which is a two-body interaction. And that tends to perturb their eccentricities and cause them to diffuse to other eccentricities through a random walk process. And so you can see, as illustrated on the plot, things evolve from the one-to-one line down vertically because they're changing their eccentricity much faster than they're changing their semi-major axis. And if they are stars, what's going to happen to them is their pericenter is going to hit the tidal disruption radius, and they're going to do that at pretty high eccentricity, and so we'll get a tidal disruption event. And because there's more stars and more volume in the outskirts, they're predominantly coming from large radii. However, if you have a stellar mass black hole, and it's coming from a bit further in as it diffuses in eccentricity, it comes down, and then it hits that light blue angled line where the gravitational wave timescale for decay is equal to the two-body interaction timescale. And so you're going to lose semi-major axis from gravitational wave radiation, and you're going to circularize your orbiter faster than you're going to get hit by something else that messes up your orbit. And so you will go horizontally on the graph, and you will end up as an extreme mass ratio in spiral. So this is the theory. And you can see that there's some critical radius around the nuclear star cluster where things tend to become EMRIs. And I want to highlight a point that I think a lot of people here will know, but maybe some folks will not, that just because you have an extreme mass ratio merger does not mean you have an extreme mass ratio in spiral. If you have something that is a stellar mass black hole and it experiences a TDE-like interaction, then what's going to happen is the tidal disruption events, they make one pass at high eccentricity, their first pericenter passage, and they're wrecked. If it's a stellar mass black hole, it may plunge directly over the event horizon, and you don't get lots and lots of orbits, and so then the signal-to-noise ratio is terrible, and we don't see it. So TDEs are more like plunges, which are the bad things from our perspective. You might imagine that there could be slow disruptors, but they have to come in on more circular orbits to start with. So this is one main mechanism, and it's the mechanism that a lot of people spend a lot of time considering. There's also another mechanism. All of those orbiters were singletons. If you actually turn them into binaries, then the tidal disruption radius for the binary is larger than for a star. And you can split the binary, and you can cause it to dissolve and evolve similarly. And you can see where the dissolved binaries end up. Some of them will end up on TDE producing orbits, and some of them can actually end up on EMRI producing orbits. But they start out in a much more favorable circular type situation. And so if you have a lot of binaries, then those are things that are better at producing EMRIs, and this is going to come up again. Okay, so what we all really want to know is what is the rate of EMRIs that we're going to see? This depends on a lot of things. It depends on the supermassive black hole mass, and in particular, its distribution out to redshift 4.5. You can see what varying that distribution does if you go check sort of the canonical Babbitt paper from 2017, and if you play around with it, you can get very small and very large predicted rates. You also need to know what the radial distribution is in your nuclear star cluster. That's going to influence your plunge to EMRI ratio. So again, plunges are bad, EMRIs are good, sort of. We'll get to that. Many people have tried to tackle this problem. Every time somebody comes out with a new paper and develops a slightly more sophisticated model these days, it feels like it sends the EMRI rate up and the plunge rate down, which is good, maybe. You also need to know what the mass distribution is. That's going to depend on the initial stellar IMF, among other things, that we're not super well constrained. Nuclear star cluster IMFs might not be normal. But fundamentally, we want to know what the black hole to star ratio is, and it's very difficult to measure that without LISA, but you could probably do worse than assume that it's whatever it is in the field. You also would like to know what the binary fraction is. As I mentioned, the Hill's mechanism does a really good job of making nice, fat, circular EMRIs. But that depends on the velocity dispersion in your nuclear star cluster, because whatever your natal binary fraction is, you can disrupt it. So all kinds of fun here. Also, generally, relaxation theory assumes spherical symmetry. We're pretty sure nuclear star clusters are not spherically symmetric, and when you include triaxial distributions, you get, again, more EMRIs. You also need to think about, when you're considering relaxation theory, how long does this nuclear star cluster live. And of course, you know, okay, they live for a Hubble time, kind of. But what I really mean is, how long are they relaxing in isolation? And so how often do you perturb the distribution of orbits in the nuclear star cluster? And there's two really major perturbations that people have thought about, right? You can make an SMBH binary, which I'm not going to talk about at all, sorry. And you can also drop a gas disk on its head and make it an AGN. And so these are two pretty important perturbations that we know happen. Oh, I forgot. These are black holes, so we have to care about GR. So it turns out that the story I told you about relaxation theory, where EMRIs only come from inside a certain critical radius, it's not true. There's this new class of cliffhanger EMRI that people have been looking at. They've realized that when you actually do the orbits using GR instead of Newtonian, you get EMRIs actually out from these large radii where the TDEs are coming from as well. Cool, so rates. You go in the literature and you're like, what is the rate? And the answer is somewhere between 1, which is implicitly, of course, plus or minus 1, so it could be 0. But I don't think it is. And now we're seeing estimates of rates as high as 10 to the 4 in a 4-year LISA mission. And I just want to highlight that every time somebody looks at a detail, it feels like we get more EMRIs, not less. And when we are talking about 10 to the 4, the waveform people say, please put some of those back. I don't want them, because now we're going to have an EMRI background problem. And I think that there is an increasing likelihood that that is the universe that we live in. Sorry. Because the background is a problem. It has the word problem right in the title, although it's a nice problem to have, but still, it's something that we need to start paying much more attention to. Okay, so how far should we trust our relaxation theory? Tidal disruption events are conveniently electromagnetically observable. And so you might have heard that there are TDE rate calculations. The predictions more or less match the observations, as long as you count infrared TDEs and as long as you are counting not post-starburst galaxies. So the post-starburst galaxies are certainly perturbed. And so now we come to the question, so post-starburst galaxies have a much higher rate of tidal disruption events than normal galaxies. And so we know that perturbations can drive up these dynamically triggered events. So I'm going to talk to you, this is why I got voluntold to give this talk, because I care a lot about AGN disks and the things that might live in them, which include stars and stellar mass black holes. They represent a major perturbation to the nuclear star cluster. They act as a dynamical coolant, and they are conveniently electromagnetically bright, so that means we can study them before LISA launches. So AGN do make EMRIs and tidal disruption events, and that's really cool. However, one of the reasons why people get very excited about studying EMRIs is because they probe the space-time in the immediate vicinity of a supermassive black hole to exquisite precision. We will be able to do amazing tests of GR. However, it would be good to know if the deviation that you're measuring in your waveform is worth a Nobel Prize or you just had some gas. And tidal disruption events are cool, but mostly people don't look for them in AGN because AGN are already super variable, and so why would we bother? That's just a pain. The problem is that the wet EMRI rate, which is to say the AGN-triggered EMRI rate, should exceed the dry EMRI rate potentially by a couple of orders of magnitude. There's a few sources of these. Some of them might, in the end, turn out to be plunges. Things that start out in the disk that are retrograde and embedded may end up as plunges. But it is particularly important to note that these things happen disproportionately in young AGN because you've just kicked the nucleus pretty hard, dynamically speaking. So if we look for markers of youth in an AGN, that may guide us to whether it's disproportionately likely to be an EM counterpart of an EMRI source. And I don't have time in my 25-minute talk to explain what a migration trap is, so you can ask me. I'm planting a question right now. If there's no migration traps in AGN disks, then prograde embedded EMRIs generated by AGN should come in at eccentricities really close to 0 and inclinations that are pretty coplanar with the disk, although GR can drive that up. And if there is a migration trap, then you can also reasonably expect to get an intermediate mass ratio in spiral out of many AGN. And so that's still exciting for LISA and not terrible. Okay. So AGN are, of course, as I said, inherently multi-messenger sources, which is great. LISA is going to localize EMRIs to certainly better than 10 square degrees, in many cases maybe less than 1 square degree, plus we've got a distance measurement to it, but that's still not going to uniquely identify what we're looking at, because there's a lot of AGN in that kind of error volume. Never mind the normal galaxies. So it might be good to know what the EM signatures of EMRIs might look like. And so this brings me to this new phenomenon, quasi-periodic eruptions. You can see the plot of the first discovered one just from 2019. And you can see what you're looking at is a light curve in the X-ray. These are repeating flares, quasi-periodic. They show up in the soft X-ray. Their repeat periods are on the order of hours to days. And each flare is sort of 10 to the 42 to 10 to the 43 ergs per second, and they occur around 10 to the 5 to 10 to the 7 stellar mass supermassive black holes, and they occur in nearby galactic nuclei. So this is kind of exciting. What are these things? Well, they're so rigorously periodic that people are pretty strongly suggesting that they have something to do with something orbiting that black hole. So this is obviously LISA candidate source. One idea, I took this particular very nice sketch from Itai Lineal's paper, but it illustrates the general sense of things. You have a star, and it is a star, not a stellar mass black hole, because stellar mass black holes are really small, and they don't present a very large face to a disk. But if you have a star that's orbiting perpendicular to the disk, every time it hits the disk, there's an electromagnetic counterpart. And people have suggested that this is exactly what's going on. So you have a star that's orbiting your supermassive black hole, and it's striking the disk, and that's what's causing those flares. Okay, what disk? I was talking about AGN, right? It's not an AGN disk, except sometimes it is. So it's probably a star or potentially a tidally disrupted stream from a star hitting a disk. Some people have suggested it's a disk instability, but that timing is really suspicious. And so even if it's a disk instability, it could be triggered by something orbiting. It's often not in an AGN, although there are some, but they are often in tidal disruption events or places that had a tidal disruption event recently. And so the disk that is being struck is not an AGN disk, but a TDE disk. So you have a star that got shredded, forms an accretion disk temporarily. What's the rate of these things? The rate of QPEs is, let's call it 1 by 10 to the minus 7 per cubic megaparsec per year. Depends on how long you think these live. We've only been watching them for like 6 years. So, 10 years might be a good guess for the lifetime. But what's really interesting is when you have a TDE, how often do you see a QPE? And so this is a conditional probability plot here on the right from Chakraborty, and they find that if you've had a TDE, you have a 10% chance of having a QPE thereafter. And so it suggests that what is happening is that you have a nucleus that's experiencing some kind of perturbation, or maybe this is just relaxation. And so you have some object, a star, that is orbiting on a pretty close orbit, long-term stable, semicircular, not super high eccentricity. Sounds kind of like an EMRI, although not quite in the LISA frequency band. And then a TDE comes in and sort of lights it up and makes it visible to us. If this is true, we're in for a really large, potentially large EMRI rate. But QPEs are almost, but not quite, the EMRIs that we are looking for. They are stars, and they are at slightly more larger semi-major axes, but they are dynamically really similar to what we're looking for, and they have this convenient fact that we can go looking for them and count them now. Okay. There's another thing that might be a signpost for exciting EMRIs and the dynamics of nuclear star clusters, and these are changing look quasars. They are also observationally identified. They're also called changing state, and really at this point we've expanded it to AGN. They don't have to be quasars. They can be Seyferts, whatever. Basically what defines them is that they have large changes, a factor of 2 or more, in their flux over short timescales that are too fast, and these are identified often spectroscopically, but now there's more photometric efforts, and these happen in sort of 10 to the minus 5 of AGN per year. And the reason why I'm talking to you about them here is because I have a proposal, which is that when you drop an AGN disk onto the nuclear star cluster and you have a tidal disruption event in that disk, then that is going to look different than a tidal disruption event in a bare nucleus. In particular, because you have gas in the inner regions, depending on whether your star arrives to be tidally disrupted prograde or retrograde with respect to the disk, that tidal stream that is going to be ripped out is going to interact with the disk. And if, for example, if you have a retrograde tidal disruption event embedded in a disk, it tends to cancel, the stream cancels the angular momentum of the pre-existing disk gas and causes it to slump in on very short timescales. And I just want to, for folks who are not AGN folks, I want to point out that sort of the typical thin disk approximation says that you can move mass around in the inner regions of AGN on a viscous timescale, which is generally hundreds of years, and we are seeing major changes in the fluxes of these objects on timescales as short as 60 days. We're orders of magnitude out. So one way to move the mass around fast is to throw some chunk of it that does not care about the disk. And you can throw a star, you can also throw a stellar mass black hole and move some of that mass around. So together with collaborators, including Barry McKernan, we had this proposal in 22, and almost immediately somebody found, the TDE people had been looking, so Cannizzaro, and they tossed this in the trash because it was an AGN and their pains, so forget it. But you can see that the AGN sort of had a very steady flux, has a giant flare, and then the flux drops afterwards, again to a steady rate, as though a chunk of the inner disk was cleared out. So you toss a star in, you accrete a bunch of gas really fast, and it takes the viscous timescale to refill. So cool. There's also another great example that you can ask me about, Matthew Graham. I'm on this paper. If you're the referee, please, please, please hurry up. But anyway, it's a really nice example, again, of a very big flare and a drop afterwards, and then maybe this one looks like it might have been like a repeating partial because there's those little flares in between. So not every changing look quasar is going to be associated with things in disks. They are a heterogeneous class, but some of them probably are. There's a bunch of acronyms that I am not going to have time to get to because I am almost out of time, but I will mention them. So we also see in AGN quasi-periodic oscillations, quasi-periodic outflows. You can read about both of those in Sakova 24. We also see things we call anomalous nuclear transients, extreme nuclear transients, repeating nuclear transients, of which QPEs are one source. But the point that I want to make to everybody here who doesn't care about AGN, because you will, is this plot from Hinkle that shows you the characteristic timescale in days of a flare that happens in a galactic nucleus and the characteristic peak luminosity. And you can see in here, there's supernovae, there's tidal disruption events, there's superluminous supernovae, and then up there in the corner, there are these extreme nuclear transients. They're definitely not like weird flares from magnetic fields, okay? There's something big, and they're powered by a big energy source, and the biggest energy source in a galactic nucleus is throwing something into the supermassive black hole. So we're going to learn a lot more about these before we launch LISA, which is good, but a little scary. One thing that I do just want to give a shout out to my team here, population synthesis is definitely going to be one way that we can tackle this to connect these different populations, because ultimately it's the nuclear star cluster that's powering all of them. And so if we get any information about nuclear star clusters, that's good. And so if you would like to do population synthesis in an AGN disk, you should use McFacts. And I forgot our swag, so email me if you want a sticker and a postcard. You can use the QR code. The people who are boxed in blue are here. Myself and Barry McKernan are only here until the end of Tuesday, so catch us while you can, but our wonderful students are going to be here the whole time, and the people who are in red are applying to PhD programs this year. They're great, take them. But yeah, we can do EMRIs, we can also do BBHs, and if you go see Miranda's poster, they can tell you how we're going to do EMRIs. So the thoughts that I want to leave you with are the thing that we can probably do to best prepare is to understand what kinds of EMRIs we are going to see, because I think that we are going to see a lot of them, and they are going to be diverse. And so our goal is going to be to figure out what kinds of EMRIs go with what kinds of sources. And that's something that we can make progress on without the gravitational wave signal just yet. And I also want everybody to think about what happens if we have too many, because I think that that might end up being the universe that we live in. And it keeps me up at night, and I'm sorry if I'm about to cause you all to stay up late at night worrying about it too, but that's how we are going to fix it before we launch. Thank you.
Thank you, Saavik. I'd like to take questions. Oh, there are many. I saw that hand over there go first. Can't see. Maybe Neil. Please wait for the microphone before you ask anything.
Yeah, I think a lot of us would take a background over 0 as the preferred EMRI rate. I mean, the background, you can have some unresolved confusion, but still there's going to be, you know, some are always going to stick up above that and be resolvable. And so it would be nicer to have a larger population, and then we'll always then have some that we can actually individually resolve. So I'm rooting for the background.
Awesome. I'll remind you said that. Tyson and Shane.
I'll also wave the flag for backgrounds are good because they're astrophysical signal. So, you know, the question of rates always kind of stands around these things we can see, TDEs, you know, QPEs, and we think they're stars. But the EMRIs themselves are going to be much more compact objects. So,
yep.
So what's the, is there work being done, or do we have a handle on what the IMF is going to be? Because that's ultimately, I think, the biggest thing that's going to point towards the compact population we need to know about for the EMRIs.
So I would argue that the IMF is important, but not, what's really important, right, is how much mass segregation happens in the relaxed nuclei and what is the radial distribution that comes out. Because really, you can get a very different radial distribution for the black holes, the stellar mass black holes, than for the stars. And so, for example, even doing things like measuring isophotes of really nearby galactic nuclei and figuring out what the nuclear star cluster's distribution is from that, or trying to, doesn't necessarily give us an unambiguous handle on what the EMRI distribution will be, because the stellar mass black holes are still invisible. You know, I would love to see, for example, evidence of the perturbations of orbits around Sagittarius A star due to stellar mass black holes there. That could give us something. Although again, as I like to say, since I remember before we knew that there were exoplanets for sure, n equals 1 is a dangerous sample size, but it's better than n equals 0. Tyson?
Yep. Okay, I'm going to ask you what you mean by a confusion of EMRIs. So what criteria are you using to decide that they're confused? We can resolve 10 to the 4 galactic binaries, and EMRIs are kind enough to go away after a while, where the galactic binaries aren't. So are you sure they're actually confused?
No, I'm not. So maybe we're okay. Maybe this is like, you know, a great problem that we will all be grateful to have in the long run. But yeah, I just calculate rates, man. I'm just going to tell you how many there are. You tell me how many is going to be a pain. If you say 10 to the 4 is okay, then awesome.
All right, I think we have time for about one more question. And if not, thank you. We'll move on.
All right, thanks.
All right, so we're going to proceed next with Chiara Caprini, talking about cosmology with LISA.
We went for view full screen.
Go, and then I'll make this go away. Okay, interesting.
Okay, hello everyone. So first of all, I would like to thank very much the organizers for giving me the opportunity to tell you about this biased review on cosmology with LISA. And it's not going, yeah, okay. So, LISA, it has not been designed to do cosmology. It has been initially conceived as an astrophysical mission, right, as we all know. However, as we will see, hopefully I will be able to convince you during this talk, is the fact that it can provide information on a variety of scales, from the galaxy to Hubble scales, and also on a variety of times, from present time to the very early universe, and therefore it can be used as a cosmological observatory. So in particular, it can test the very early universe by possibly detecting a stochastic background, if it is there, and therefore this will allow indirectly to test high energy phenomena. And also it can test the late universe through the observation of gravitational wave emission from compact binaries, and therefore test the universe expansion. Okay, so I'm sure you are more or less all familiar with this picture that is a cartoon of all the possible LISA sources that we expect LISA to see from the Red Book. For the rest of this talk, I would actually proceed source type by source type, and every time I will highlight their use for cosmology. And as we will see, there are sources that we can use to probe the late-time universe expansion. I will go through the possibility of detecting a stochastic background from the early universe, and as we already heard in the previous talk, we will see that there are also sources that generate foregrounds, masking other sources. So whenever appropriate, I will also try to give you some information on the LISA figures of merit for these particularly cosmology-related science objectives. So what are the figures of merit? These are tools that have been developed by the LISA community. In particular, back then was the Science Investigation Work Package with the help of some scientists in the LISA consortium. And these figures of merit are meant to assess the ability of LISA to achieve its science objectives. So basically, they are designed to evaluate the impact of a change in the LISA sensitivity on the scientific performance of the instrument. And right now, so these were developed quite a few years ago, and right now the LISA science team is reviewing them and selecting some of them and also probably expanding others as part of its work. And there is also a paper, hopefully complemented with pipelines, which will come out soon, and is coordinated by Riccardo Buscicchio and Alberto Mangiagli. And here what I will be telling you about figures of merit related to cosmology, cosmological scientific objectives with LISA will be taken from the draft of that paper. Okay, so let's start with the binaries in the galaxies. Unfortunately, so there is a lot of great science that one can do with the compact binaries in the galaxies with LISA, but for cosmology, they are important only because they generate this confusion noise here at low frequencies. Now, the question we need to ask from the point of view of the cosmologist with respect to this foreground noise is how we can handle this. And the great advantage that we have for astrophysical foregrounds with respect to cosmological backgrounds that we will see later on is that we do know at least some information, we at least have some information on the astrophysical populations that are generating these foregrounds. And therefore, we hope to be able to have a prediction of the spectral shape of the different astrophysical foregrounds. And this prediction of the spectral shape can be used to detect the signal and therefore then go look for something unknown behind this signal. So typically, we want to ask the question how to distinguish the galactic foreground from a possible stochastic background. And in the case of the compact binaries in the galaxies, we can fit a multi-parameter spectral template, and very welcome, we would like to also exploit its time modulation, early modulation. Now, going to massive black hole binaries, these are much more interesting from the point of view of cosmology than galactic binaries if they are accompanied by electromagnetic counterparts. And we already hear that this is most probably the case. They are expected to have counterparts if they occur in gaseous disk at the center of galaxies. And as you all know, there is a very important test in cosmology, right, which consists in fitting the Hubble diagram, so the luminosity distance versus redshift relation, because this particular relation depends on the Hubble factor and therefore depends on all the cosmological parameters, okay? So when we reconstruct the Hubble diagram, we are able to test the content of the late-time universe. And actually, massive black hole binaries with LISA can be used as bright standard science to measure cosmological parameters. And here we have an example with the candidate, with the simulated events on the luminosity distance versus redshift diagram. Now, the fact is that in order to be able to use massive black hole binaries as standard science, they absolutely need to be accompanied by an electromagnetic counterpart, because the gravitational wave measurement alone does not provide an independent measurement of the redshift, right? Because in the waveform, we have here a very clean and direct measurement of the luminosity distance, but the redshift is hidden into this combination of the redshifted Chirp mass. So we need to get the redshift from an accompanying counterpart. And this clearly means that only events with good enough sky localization can be used with electromagnetic counterpart for this exercise of reconstructing the Hubble diagram. The nature of the electromagnetic counterpart at merger is also not very clear so far, and it is important to keep track of weak lensing, because this is perturbing the error estimation of the luminosity distance from LISA. So in a set of papers here, we constructed an approach, a method to try and assess the ability of LISA to test the late-time expansion of the universe. And we started from catalogs of massive black hole binaries from simulations. We, of course, apply the LISA beta code to get the sky localization error and the luminosity distance error. Then we have sort of invented a way in which we could detect a possible electromagnetic counterpart starting from the information on the gas that we had from the simulations, and in the end we construct the Hubble diagram. So the number of standard sirens is actually quite low, especially for 4 years of the mission, and depends heavily on the massive black hole binary astrophysical generation channel. But what is extremely important for us cosmologists is that these events, as you can see here, with this distribution of the average number of electromagnetic of events with electromagnetic counterparts, they cluster at high redshift, so redshift between 2 and 5. This is very good for cosmology because it's complementary to standard cosmological probe that in general probe the expansion of the universe at redshift smaller than 2. So the uncertainty of this cosmological measurement is very difficult to forecast because the errors are actually dominated by the statistical fluctuations in the realization of the massive black hole binary catalog. So in general, what we do is always that we quote errors that are true for 50% of the realizations. We had many universe realizations in this work. And with that, LISA can have a constraint on H0 of 5% in 4 years and 2% in 10 years. But as I told you, the real peculiarity of this is that LISA is able to probe the expansion of the universe at high redshift in a way that is complementary to standard cosmological probes. So we did explore a couple of high redshift models, and the first one was assuming that the universe is matter dominated, which is something pretty logical at redshift about 4, and there you see that we can have a 10% error on the Hubble parameter, 6% in 10 years, 3% on the luminosity distance, and here are really numbers that start to become competitive with cosmological, future cosmological observatories that are able to probe the expansion at high redshift. We also considered a model-independent scenario in which we fit the luminosity distance with some splines, and here as well, the errors are quite promising. Okay, and we have actually 3 figures of merit attached to this science objective for LISA. The first one concerns just the number of massive black hole binaries, because this is a model-independent figures of merit. So you see it is based on how many massive black hole binaries are detectable with SNR larger than 10 and sky localization at mergers smaller than 10 degrees squared. And here each FOM is a traffic light in which you see blue is when the scientific objectives is very well met, green is okay, yellow starts to be in danger, and red is when the science objective is not met. And then here we have other 2 FOM. One is directly on the error on the H0 in order to be able to explore the Hubble tension, and the other one is on the error on H at high redshift. Now we go to extreme mass ratio in spirals. We already had a very, very nice review about these sources. So for cosmology, indeed, as we heard, they can be problematic because they can produce a dangerous foreground stochastic signal, okay, that will mask other sources, deterministic sources, but also a possible cosmological background. But what is actually positive, especially if they are numerous, is that they can be used as dark sirens. So dark sirens are sources for which there is no electromagnetic counterpart that is expected, but the redshift can be still inferred with a statistical method. So you cross-correlate the gravitational wave measurements with some galaxy catalog. Okay, and in this case, this paper pointed out that EMRIs can be used to this scope if they have a high enough SNR and they are close enough, at redshift smaller than 1, to be able to cross-correlate with galaxy catalogs. And because these sources are at low redshift, what is important is that they can provide also a constraint on the equation of state of dark energy, which was not possible with massive black hole binaries because they were clustering at too high redshift. We have one figure of merit concerning EMRIs here, and this really goes just with the number of these kind of events with high SNR and smaller redshift that we can detect and infer then an error on H0 to explore the Hubble tension. But in reality, the full potential of LISA to probe the late-time acceleration of the universe will be exploited by combining these two populations, which, as we have seen, are nicely complementary in terms of redshift distribution. And here you see how combining these two, the measurement on H and omega m from these two populations can actually reduce very much the degeneracy. And we might aim at a famous sub% measurement of the Hubble factor, which is what would be, will allow us to dig into the problem of the inconsistency between the Hubble measurement between high redshift and low redshift probes. Okay, another source that I want to discuss here, which is not in that cartoon that I showed at the beginning from the Red Book, because this source has been revisited lately, actually, are extragalactic white dwarf binaries. So these are important for cosmology indeed, because apparently, since we don't know yet very well about the EMRIs rate, they have they constitute the most dangerous foreground that we can have for cosmology. They are obviously is a stationary and isotropic foreground because these are extragalactic white dwarf binaries, and this is what renders it very difficult to tackle when we want to go look for a stochastic signal from the early universe. So this paper here, from this paper here, I've taken this cartoon in which you see the variability that one can have on this foreground depending on the population assumption in the population, and they propose this particular parametrization for the spectral shape. And so you see that for some models, actually, this particular foreground touches the LISA sensitivity, while this is the power law integrated sensitivity. We do have a figure of merit also about this foreground. And the figure of merit actually constitutes, deals with reconstructing this particular foreground based on the fact that we do know, or at least we can model its spectral shape. So in this particular figure of merit, what we do is that we keep the noise free. The LISA instrument noise, there is no parametric dependence on it inserted in the MCMC search, but it is modeled as simply as splines, and instead what that is modeled with a parametric dependence is the extragalactic white dwarf foreground. Okay, and here we see that even with this freedom on the noise model, there is the possibility to reconstruct our foreground. This is the galaxy, and we do have some thresholds on the possibility to reconstruct the foreground with here thresholds that are based on the fact of whether or not one can infer the characteristic of the population. Okay, and now let me come to the stochastic background from the early universe. This is the absolute dream for a cosmologist to be able to detect something of this sort. Now, why is that so important for cosmology? Well, the fact is that everything we know about the birth and the evolution of the universe comes from the detection of electromagnetic emission, and in particular the cosmic microwave background. So with the cosmic microwave background, we were able to access the status of the universe up to when it was 380,000 years old. And of course, we could also infer information on the very early stages here about inflation through the cosmic microwave background anisotropies. However, if we have a stochastic gravitational wave background, this gives us the possibility to look much earlier in the evolution of the universe. So stochastic backgrounds are a fossil radiation that can beat the electromagnetic horizon that we have in the universe, right? And therefore, it allows us to peep into the first stages of the universe evolution, which contain potentially revolutionary information on physics. So why are the signals from the very early universe stochastic backgrounds? This is due to the causal nature of space-time. Okay? So you imagine that today we have a detector here, LISA. It is able to detect in its past light cone. Now, this past light cone will intersect the constant time hypersurface at which the gravitational wave source is operating. And here I'm looking really into the very early universe, so something like when the universe had an age of a picosecond, about a few picoseconds. Okay, so the detector will access a region which is composed by many, many causally disconnected regions. Because from the sort of beginning of the universe, time zero, there was only a finite time to put regions in causal contact. Okay? So if we look at the angular size of the sky today, with respect to the angular size of the correlated regions from a source of gravitational waves at this early epoch in the early universe, there are about 10 to the 24 causally correlated regions into the field of view of LISA, which is not 360 degrees, it's about 10 degrees squared. Okay? But still, so very many LISA, what we'll access is the gravitational wave signal from very many causally disconnected regions. And this clearly produces an uncorrelated stochastic signal. Now, the key point here is that the size of the correlated region, okay, is actually connected with the time at which the gravitational wave source is operating in the early universe. And this then determines the characteristic frequency of the signal. And so here you see, in terms of omega gravitational waves as a function of frequency, a possible signal from the early universe, okay, peaking at a characteristic frequency which is related to the size of these causally correlated regions, okay. And the amazing serendipity of LISA is that this millihertz frequency band, in which it is the most sensitive, corresponds to an epoch when the universe had an ambient temperature of about 1 tera-electron-volt. And this is exactly the energy threshold that separates, is the frontier between tested physics at colliders and new physics that we don't know what it is beyond the standard model of particle physics. At that time, the universe was dominated by the X field, which was performing its symmetry breaking and giving masses to all known elementary particles. So it is a serendipity that this millihertz region corresponds to this very interesting epoch in the early universe, which is really a frontier of our knowledge today. So stochastic gravitational background, I mean, we don't have them just from that epoch. We have many proposals and can inform us on how the universe has begun and on the fundamental laws of the physics that governs it. Therefore, they harbor an amazing discovery potential, okay? Indeed, offering the opportunity to test beyond our knowledge of the fundamental laws of nature. However, exactly because these are based on theories that so far lack experimental confirmation, it is impossible to make a definitive prediction of the signal. So we don't know what we are looking for. There is a great variety of spectral shapes that are proposed from a great variety of sources. You see here this cartoon, which is some of them very high, with very high signal-to-noise ratio possibilities. But there is here an outstanding challenge for LISA, which is how to distinguish these particular proposals of signals from the instrument noise. and also from astrophysical foregrounds. Now here I just want to flash one case in which it actually works. This was the signal that I showed you in the previous slide as well. And for this particular case, you see the signal-to-noise ratio is quite high, and it is possible to reconstruct the parameters determining the signal. Of course, why it is possible to do that? Because here we are actually performing a template-based search of this particular signal, knowing its spectral shape, and we also are assuming some knowledge of the noise of the instrument. We assume a two-parameter noise model of which the parameters are fit alongside with the parameters of the signal. But if something like that occurs and we are able to reconstruct the parameters of the signal, then the parameters determining the gravitational wave background can then be mapped to those of the particle physics model that is underlying this signal. And therefore, you see here an example in a particular extension of the standard model. Now here is no longer gravitational wave amplitude and frequency, but the actual parameters of this model, the mass of the singlet, the coupling between the X of the singlet. This is what LISA could be probing in this particular scenario, and this is the region that is probed at particle colliders, present and future. So you do see the possibility of complementarity here. Now we have also a couple of figures of merit attached to this particular science objective 7. And these figures of merit are actually all focused on the fact, are we able to assess the presence of some unknown extra noise component? And if the answer is yes, are we able actually to reconstruct the spectral shape, which is the only handle we have to actually infer the origin of this signal, okay? So the first FOM is based on the work by Nikos in this paper, and it really asks this question whether we can recognize the presence of an extra noise component, giving a certain percentage of assumed knowledge of the noise of the instrument plus the foreground, that here we fix to 20%. And here you see, so the benchmark signal that we have assumed for this particular FOM, and depending on the uncertainty that we allow on the noise plus foreground component, how much of the frequency range of this signal we are able to assess, saying, oh yes, in this frequency range there is something more than what we just expect. Okay, and the FOM is constructed indeed depending on which percentage of this frequency range allow us to map the particular benchmark signal we have adopted. And as you can notice, there is no red in this FOM because we are not sure that this signal is there. Sorry, I will speed up. So this is my last slide, actually. And here is the second FOM associated to this particular science objective, in which here we say, okay, the first FOM gave us a yes, we are able to distinguish the presence of this signal. Now the second question is, are we able to actually reconstruct the spectral shape in order to be able to infer where this signal comes from? And here we proceed through, we divide the frequency beams, the frequency range of LISA in beams, and in each beams we fit a power law, and then we have an FOM that tells us, okay, are these power laws good enough to give us an information on the shape, spectral shape of the signal? Okay, and here I leave you with my conclusions. So just one thing, I hope that for not having been designed to do cosmology, LISA performs pretty well. Thank you.
All right, I'm sure we have questions. Saw yours go up.
So maybe I have a question a little bit beyond LISA. So you say that there is this serendipity of the milliards corresponding to 1 tera-electron volt, and so this is something that seems to be a very special zone. So if you, and also let's assume that you cannot claim a detection in LISA because you actually have very difficult time in saying what will be the noise, in measuring the noise. So if you can measure the noise in a future mission, you will go for the milliards one because of this serendipity thing, or the uncertainty is such big that you don't know exactly what will be.
So, okay, first comment is these milliards actually, you know, the range is from 10 to the 4 to, let's say, 0.1, and this gives you access to a quite wide range of energy scales, up to 100 TeV, okay, so it's already very good what you can do. The answer is yes, I would go for the milliards because I think this is really very well motivated, okay, scientifically. Then we, you know, it depends because I don't want to go into the detail, but this peak frequency is also determined by other parameters, and therefore this can shift. So I think we can do something very well also with a Deci-Hertz mission or a microhertz mission. And I would like to add something which is also very interesting is that pulsar timing arrays with their nanohertz frequency, they probe the QCD phase transition in the early universe, okay? So we do have this amazing serendipity, LIGO Virgo Kagra or Earth-based interferometers, they probe the Peccei-Quinn phase transition. It's something really strange that, you know, for completely independent reasons, we do probe very interesting epochs in the early universe.
Thank you for that. My mind was blown by the stochastic gravitational wave background stuff. My first thought was that we should sell LISA not only as this amazing gravitational wave detection system, but also as the upgrade to CERN that will never get built. And we're getting it for free. This is incredible. I'm amazed. So my question is, how far back can we realistically test beyond the CMB background, right? You mentioned 10 to the minus 11 seconds, which is insane. But like realistically, like what do we think we can confidently get back to? Is 10 to the minus 11 seconds a reach? Is it plausible?
Okay, thank you very much. Yes, so I'm from CERN, so I do hope that the FCC is going to be built, but for sure the time scale is much longer than LISA, so that's absolutely something positive to say. Now, to how far back? So, in principle, theoretically, we can go up to the Planck scale. It's really, we can see the entire, you know, the entire range of scales up to a scale that we don't even know what the physics looks like there. Of course, there is inflation, which is at a lower energy scale, so this is going to be our horizon. Now, the real problem is not how far back we can see, because that's okay. The real problem is not how many proposals we have, because, you know, people have been investigating this. The real problem is, once we detect something, are we able actually to say that it is something that is not astrophysics, and which kind of source is generating this? And for that, I mean, I think for LISA at least, just for LISA, the answer depends on the signal-to-noise ratio. Because if we have a signal-to-noise ratio of 1,000, for example, for cosmic strings, then in that case, I don't think that anyone would realistically believe that this is extra noise, right?
I did want to do a quick check-in with our web participants. Do we have any questions from over there? No? All right. I think let's thank Chiara again.
Thank you.
So next up, I believe our next talk is a remote talk from Rita Dolesi at University of Trento. Thank you, Peter. Yeah, maybe Rita, we could do an audio check. Can you say something?
Can you hear me?
Not quite, maybe faintly. Can you keep talking?
Can you hear me? Can you hear me?
There we go.
I think that sounds good.
1, 2, 3, 4.
Yeah, anybody wave your arms if you can't hear? We all good? Maybe, do we have control of the volume? A little bit louder might be nice. If you
1, 2, 3, 1, 2, 3.
Perfect. Thank you.
Okay. Okay. Good morning. Good morning to everybody, and thanks a lot for inviting me to give in this talk. I will give this talk, of course, on behalf of the overall GRS team that is working on the gravitational reference system. So the gravitational reference system is considered the most critical hardware element for the free fall performances of the test masses that acts as geodetic reference bodies in gravitational wave detection. And as such, it ultimately determines the sensitivity of LISA in the low frequency region of its measurement band, where a significant fraction of the mission expected scientific return is expected. For the newcomers, I will spend a few words explaining why the acceleration matters at low frequency, which is the role of the drag-free loop, and I will provide a simple explanation using a cartoon. So in all implementation of the LISA concept, a detector arm is made by two satellites that basically send each other a laser beam. Propagating throughout a gravitational wave curvature, beam accumulates a time-modulated frequency shift. But acceleration of spacecraft relative to the local inertial frame also shifts frequency via standard Doppler effect. And very noisy satellite acceleration with respect to the local inertial frames will spoil completely the sensitivity to the gravitational waves. So it must be subtracted. For this reason, each satellite basically hosts nominally free-falling test masses with a much smaller spurious acceleration with respect to the inertial frame. Relative to these test masses, the satellite acceleration along the link direction is measured basically by means of a local interferometer and subtracted. Then the challenge becomes to suppress this residual acceleration of the test masses by decreasing the stray forces acting on those test masses. In addition, we have to take care of the fact that the satellites are pushed by external forces and would hit the test mass. So this is the role basically of the so-called drag-free control strategy, where the position basically of the spacecraft relative to the test mass is measured by a local interferometer, and these signals drives thrusters in order to keep the spacecraft test centered on the test mass. With this control feedback, the acceleration of the test mass will be then made by a term that is due to the stray forces acting on the test masses, and there is also this additional term that couples the test mass by means of spring-like coupling to the residual test mass shifter. Actually, in LISA, the situation is more complicated, because you have to do this along two non-orthogonal axes, where you basically, the spacecraft is following the test mass 1 along the interferometer's axis 1, the test mass 2 along the interferometer axis 2, while on the other degrees of freedom, you have to apply electrostatic forces in order to keep the test mass centered. At the end, you have a combination of three interferometric measurements. So you have the long arm interferometer that brings the information, the measurement of the strain of the gravitational wave. but also the disturbance due to the stray acceleration of this spacecraft. But with the two local interferometers that are measuring basically the relative acceleration between the test mass and the satellites, you can combine these signals to subtract basically the acceleration of the satellites. You suppress basically these stray effects to the level of the differential stray acceleration between the two test masses. In this way, basically, you are making an equivalent direct test-to-mass measurement. But of course, this measurement is affected by several optical readout noise. It's very complicated to take care of them. But regarding what happens at low frequency, the sensitivity limit is dominated by these terms, related to the residual stray forces acting on the two test masses. In the frequency domain, a low frequency, basically the amplitude spectral density of the acceleration noise divided by the square of the frequency determines this slope at low frequency. So you have this acceleration of the test mass spoiling your sensitivity with a dependence on the frequency that is 1 over the square of the frequency. How do we know that we will succeed in achieve the required free-fall purity? There was LISA Pathfinder that was an end-to-end experimental demonstration of the free-fall test mass at the level that is needed for LISA. The LISA Pathfinder gave us an acceleration noise model for the information to build up the acceleration noise model for LISA. That is very important in order also to optimize the characteristic and the performance of the gravitational reference sensor for the LISA needs. We just celebrated the 10 years from the LISA Pathfinder launch and the success. And if you want to know more about the legacy of LISA Pathfinder for LISA and for the future precision space mission, you can listen to the talk of Daniele Vetrugno in the next days. But back to the gravitational reference system. So in order to implement, to fabricate now a gravitational reference system for LISA, the challenges are to be addressed concern optimizing the GRS implementation for the LISA requirement. And this requires to advance also beyond the LISA Pathfinder heritage. And this will be achieved through improved performance of various subsystems and through the development of more accurate models and robust ground verification strategies in order to mitigate all kinds of risks. I will focus in particular on these activities and on the most recent results from preliminary testing campaign that are part of the setup, the characterization, the commission of this new testing facility on the ground. The gravitational resonance system has several subsystems. So first of all, we have the test mass, our mirror, and our geodesic reference body. This is surrounded by an electro housing that gives the read, so the position of the test mass along all degrees of freedom, and allows also to apply electrostatic forces for the electrostatic suspension that we need. We have a caging mechanism device that discharges the test mass that otherwise would increase the overall noise with the charge accumulated by the cosmic rays. The electro housing is operating with a front-end electronics that allows for the position sensing and the actuation. And then we have a couple of mechanisms. One is used for grabbing and position and release the test mass in flight, and the other one is the so-called cage inventing mechanism. It's a mechanism that allows to keep the test mass fixed during the vibration of the launch, and then open also the venting valve to space in flight. Upgrading. So for the front-end electronics, mainly there have been some design optimization for the LISA actuation electronics, and here then we have a new test mass charge management device based on the LED UV photoelectrons. We have a new venting to space duct with a larger conductance, and we will learn about this more in this talk. And we had some delta design for the Grammy position release mechanism that gives some improvements with respect to the performance has been obtained for LISA Pathfinder. More about the evolution of the sensing actuation electronics for the GRS will be illustrated, will be given in the talk of Luigi Farraioli on Thursday. I was mentioning the upgrade that we had in the GRS subsystem, and another aspect that we had to improve was related to our ability to test requirements and performance on ground. For this, these required the involvement of different groups with different expertise to cover all the GRS verification needs. And several customized test facilities has been defined and are under preparation, as I will tell you and show you. But back to the test mass acceleration noise. So which are the forces and the mechanism that disturbs the free falling of these test masses? There are many mechanisms. Those forces depends on the physical properties of the sensor, the test mass included, of course, but it depends also on the physical properties of the environment, like temperature, gravity, magnetic field, mechanical stability. And in addition, also it depends on mode of operation and on spacecraft control scheme. Here is shown the amplitude spectral density together with the total acceleration noise requirement. Each of these noise is further broken down into several more fundamental noise effects, where the GRS is playing a significant role. Usually, and for the implementation of the GRS, we separate what we consider the noise sources that are under direct responsibility of the gravitational reference system from those that involves also the environment, and so they are under the LISA system responsibility. For the GRS, we have the Brownian noise, actuation force noise, stray electrostatic force noise. For those that are under system responsibility are mainly disturbance that are related, as I was saying before, to the environment. So how much the environment is disturbed, and they are related with the coupling with the test mass spacecraft and MOSA movement. These forces has a different role and limit the sensitivity of LISA in different frequency regions. So the Brownian noise is a limit in the region of the millihertz, while at lower frequency, other other noise sources like accretion noise, magnetic force, stray force, electrostatics, starts to dominate in the lower part of the LISA measurement band. Below the LISA measurement band, temperature fluctuation and the coupling force noise with the spacecraft MOSA sets the limits of the expected sensitivity. The Brownian noise is dominant in a wide part of the LISA band, is related with the residual gas inside the gravitational reference sensor, the residual gas surrounding the test mass, gas damping of the motion of the test mass is related with a viscous damping coefficient that is proportional to the pressure, and that gives this noisy force via the fluctuation dissipation theory as described by this formula, where you can recognize these are the mass of the test mass, the size of the test mass, the mass of the molecule present in the residual gas, but in particular we have this dependence on the pressure. This source of noise translates for LISA in a pressure requirement at 2 micropascal. While for Pathfinder, the requirement was 10 micropascal, so we decided to decrease it by a factor of 5. Why? Because we would like to keep this noise source low, because it's a dominant noise source in a wide, in a considerable, significant region of the LISA band. Decreasing the pressure decreases also another source of noise that is related with the gradient of pressure across the test mass that fluctuates because the gradients fluctuates because the temperature fluctuates, given that the outgassing is a temperature-driven phenomena. You will end up having this source of noise that is dominant at a very, very low frequency. 2 micropascal was the level of the pressure at the LISA Pathfinder mission, so 1 year and a half almost. So we are confident that we can achieve that value, also by means of a more robust vacuum strategy that we are implementing. The pressure depends on the outgassing rate that you have inside the vacuum chamber of the gravitational reference sensor, the pumping speed we are venting to space, and the external pressure that you have outside basically the spacecraft. This is the simple formula that suggests that you have to maximize, of course, the pumping speed to minimize the outgassing rate and to guarantee that outside the spacecraft the pressure is low enough. Like in LISA Pathfinder, we have a vacuum chamber and a vent valve. These allow us to perform a bake-out on ground to preserve the vacuum during the on-ground storage, and also to avoid contamination. The vacuum chamber also shields the inner gravitational reference sensor from the payload and the spacecraft outgassing, and this allows to open the vacuum chamber just in flight. New in LISA, we improved the vent duct interfaces. Now this is basically sealed onto the main body of the vacuum chamber. This allows us to preserve the vacuum from contamination, all parts inside the vent duct, but downstream of the vent valve. Here is the vent valve. So these parts here inside this body are now in vacuum during the storage. Ground pumping interface allows us to evacuate the duct on ground, and with this we reduce also the permeation across the Viton ceiling here. And in addition, we also were allowed to increase the conductivity, so to make this venting duct bigger in order to increase the pumping speed. So the approach now, our plan is to demonstrate the gravitational reference system outgas on ground and then to seal, to send it for integration at the spacecraft, and then basically to open this vacuum system, maybe during the cruise, but we are still thinking about this. Another important improvement is related with the testing and the measurement of the outgassing rates. That is very important parameter. We have two important improvement over the testing that was performed for LISA Pathfinder. We have a new facility that allows a more quantitative measurement, accurate quantitative measurement of the outgassing, and also to have information about the species. This has been developed with the support of CERN, and it's now in operation in OHB Italy. With this, we can perform a Beccai procedure and make direct measurement of the outgassing contribution, both on simple level and then at the very end of the integration of the flight models. Another important improvement is related with the possibility to pump and to perform the back-out just of the inner part of the gravitational reference sensor, so that we can isolate it from additional contamination, and also to isolate and measure exactly or more accurately its contribution to the overall outgassing rates. There are already measurements that has been performed very recently. They perform a dry run in order to characterize the level of the outgassing of the station, and then the first test was made with the electro housing cables that at the end results to be compliant with the maximum outgassing requirement. We support this effort in decreasing and guaranteeing the pressure also by means of molecular simulation with the mole flow that are developed at CERN, and these simulations are relevant for multiple aspects. I don't have time to go in detail, but this investigation includes also some simulation that regards the famous glitches that are observed in LISA Pathfinder. There will be a poster by Jacopo Ginobbi on this problem. The other source of noise that's under the responsibility of the GRS is related with electrostatics. So the test mass is surrounded by electro housing with millimeter gap size and by electrodes that are used both for actuation and sensing. Hence, the test mass is subject to a variety of effects that are induced by electrical forces. So here is the well-known formulas for the attractive force between plates of capacitors. We can expand the squared and to see which are the different contribution, where a very important role is given by the voltage of the test mass. That has a component that is related with the accumulation of the charge because of cosmic ray deposition, plus the effect of all the voltages on the electron housing. So we have a variety of noisy effects because any of these voltages can fluctuate, and also the test mass charge fluctuates. Noisy forces are due to fluctuation in the actuation driven voltage as well. And for these again, if you are interested, you will learn more in detail in the Luigi talk. Just few words about a couple of these entries that are related then with verification strategies on ground that we are implementing. One of these noise source is the quasi-static voltage that interacts with random charge noise. And here the two parameters that that are more relevant is this shot noise that affects the charge of the test mass. That is due both to mainly by the incoming energetic particles, but we have to pay attention also not to introducing extra additional noise with our charge management system. Delta X is an effective DC potential, and we are able to measure and compensate at the 5 milliwatt level. Another entry is the quasi-static charge interaction with the random voltage fluctuation. And here, basically, the fluctuation of this delta X, we think, based on the LPF experience, that will be dominated by the actuation circuitry noise, with a small contribution from the surface potential. The charge, we have to take care of the charge by means of control and charge management system. So we develop a completely new, a new charge management device based on the photoelectric effect induced by UV light. The use of LEDs allows for a nice strategy of illumination with pulsed light synchronized with the front-end electronics. This concept was demonstrated. University of Florida, NASA provides this subsystem. We received last year the TRL6 EGSC. Here are the people very happy that day. They deserve this picture because it was quite complicated to bring it inside our lab. And here there is also a picture of other people that were not there, but they serve this picture for other contribution that they give. There are several talks and posters that describe this testing activity that will be performed in Trend, also using this TRS6.
Hey, Rita,
we support the...
I'm sorry to interrupt. Yeah. I just wanted to ask you to wrap it up soon. Thank you.
Okay, I'm close to the end. So we support this new the development of this new charge management device with simulation, both to predict the propagation of the light, and given the propagation of the light to predict the performance of this discharge signature. More on this in the Valerio Ferroni talk in the next days. We develop also additional facility to characterize the UV light that we use to extract the photoelectrons. So we have now a very detailed system that allow us to characterize this the light cone of the UV light. Surface coating and properties of the surfaces plays a very important role. We don't have a clear model that guarantees this performance based on coating received or thickness or purity or reflectivity of these surfaces. So we have to rely on a very strict procurement and verification strategy that basically requires to test all the with witness sample all the surfaces that are that will be coated to have a very repeatable coating receipt and also the subsequent story of these pieces, and we are preparing an end-to-end testing at all model levels, and this will be described by Francesco Venturelli. Here, this is a facility that has been developed in order to allow us to make a quite deep investigation of the surface properties that now is giving a very nice results, showing its ability to monitor the effect of for example, bake out of the storage or went into air onto the property of these surfaces. Patch potentials. Also here, we are investigating the possibility to use Kelvin probe in order to study this, the fluctuation of these patch fields that might have been some role in the extra noise that has been detected in LISA Pathfinder. For the mechanism as well, they are developing and testing these new facilities to guarantee a more reliable performance of this system. And I want also to let you know that there is another interesting talk by Carlo Sasso about the test mass regulator that they in EMRIs are developing. Here is the summary. Sorry for being late. Thank you for your attention. And I think that the activity that is ongoing now are really preparing us for a successful GRS implementation till the flight qualification. Thank you.
Thank you, Rita. I believe we have lunch all set up. If maybe just one brief question to make a point of asking for it. Okay. Oh, yeah. Right behind you.
Ciao Rita, it's Daniel here.
Ciao Daniel.
Ciao. I have a quick question because it's the first time I see the results from the outgassing testing system. You know very well that one of the culprits of several things that maybe were not perfect in LISA Pathfinder was outgassing from cables and things like that. Do you think this test can say something on that, apart from the fact that...
Absolutely.
Thanks.
Absolutely. So for the LISA Pathfinder, we in the ground testing campaign of the outgassing rates, we performed the measurements with a method that was not accurate enough. So, but now with this system, we are much more confident that the numbers that we are obtaining are correct. And moreover, we are implementing also another procedure that should allow to decrease even more the outgassing rates. That is basically to perform pre-bake out on all the elements that will be go inside the GRS in order to reduce the overall outgassing. This seems to work, and also to reduce the risk of contamination.
All right, thank you again.
Thank you. My colleague will be happy to take further questions about all the GRS work that we are doing. Thank you.
All right, don't move yet. Our esteemed leader here, Peter Shawan, is going to make some announcements.
I'll be quick. So the afternoon, we're scheduled to start at 2. Let's please try to start at 2. That'll be in this room and then the 2 other parallel rooms on this floor. You've seen the program and the map by now, I think. So we'll try to start that at 2. For lunch, there are 3 tables that have the same food on them. And it'll work best if we get kind of 3 lines forming from this side going in. When you get to the table, both sides are available. So use both sides of the table. We'll have 6 people going in parallel to go through the table. There are drinks and desserts you can get now or come back for. Enjoy your lunch. Oh, one more thing. If you have a green card for special dietary needs, just show it to any one of the staff members. They can give you your prepared food. But feel free to also go through to the lines if there's other food that will suit you.